Hey there, folks. This is Mr. Young, and I am going to take you through a quick lesson about bond polarity, covalent bonds, and whether they are a polar covalent bond or a non-polar covalent bond. This goes along with boxes 2 and 3 in the Unit 9 Polarity Hyperdoc, bond polarity. So what does the word polar mean? The word polar, well, the Earth's magnetic field is an example of something that's polar. The Earth has a north pole and a south pole. It's different on each end. The North Pole is different from the South Pole. Opposites attract, sames repel, so north repels north, north attracts south. They are different. Earth is polar. It's different on each end. One end of the Earth is a North Pole, one end of the Earth is a South Pole. Okay? Now, in this lesson, we're going to try to apply this idea of polar and nonpolar to bonds. In another lesson after this, in a couple days, we'll analyze a whole molecule, and then we'll use the idea of molecules being polar or nonpolar to figure out some things about how molecules interact with other molecules. But anyway, polarity in bonds. What is it? Well, you might want to write some of these things down. Hit pause, grab a piece of paper, and write some of these things down. Okay, polarity is a way to describe how lopsided a bond is. And what do we mean by that? Here, remember, we're talking about covalent bonds, bonds that are sharing, but the electrons can be shared in different ways. So we're describing how lopsided a bond is and how the electrons in the bond are being shared. The sharing of electrons can be equal sharing or it can be unequal sharing. Again, remember, we're talking about covalent bonds where electrons are being shared. They can be shared equally or unequally. How do we figure this out? We use electronegativity to figure it out. What does electronegativity mean? You should remember this from Unit 8. Electronegativity is a measure of how strongly an atom attracts electrons. You can look it up in Table S. The electronegativity values go all the way up to 4.0. Fluorine has the strongest electronegativity. I also called electronegativity electron getativity or electron gravitivity. High electronegativity means that atom really attracts electrons. Okay, enough about that. I'm going to go through 3 different bonds to help you understand the ways that bonds can be polar or nonpolar. Covalent bonds can be polar or nonpolar. Okay, here we've got a bromine bonded to bromine in Br2. Okay, so there's a bond here. Okay, and then each of these bromines also still has 7 valence electrons. I'm just doing that Lewis dot diagrams correctly here. Okay, and bromine has an electronegativity of 3.0. That's bromine. Oh, this is bromine too. They have the same electronegativity. It's a covalent bond between 2 nonmetals. They have the same electronegativity, so they are pulling the electrons equally. Those electrons in the bond are being shared equally. We call that a nonpolar covalent bond. Now, one really important thing to remember, the word polar, you should associate that with being lopsided. Okay? If something is polar, it's different on both sides. So if it's the same on both sides, we say it's nonpolar. This is a classic example of a nonpolar covalent bond between 2 atoms of the same element. Okay, let's move down to HBr. HBr, hydrogen bromide. Okay, 2 electrons are being shared there. We've still got these 7 valence electrons around the bromine. There's the Lewis dot diagram. Okay, hydrogen has an electronegativity of 2.2, but bromine has an electronegativity of 3.0. They've got different electronegativities. Bromine has a stronger electronegativity. Bromine hogs the electrons more. The electrons will spend more of their time over here close to bromine. And so this is a polar covalent bond. Why is it polar? Because it's lopsided. Bromine pulls the electrons more towards itself because it has a stronger electronegativity. Now in this last bond, wait a minute. Is this a covalent bond? No. We've got potassium, which is a metal, and bromine, which is a nonmetal. So actually, let's make our Lewis dot diagram correctly. We have to use brackets. Potassium loses 1 electron to become a +1 ion. Bromine gains 1 electron, and so it goes from 7 valence electrons up to 8. Remember, we're showing the original valence shell. So bromine gets a -1 charge because it gained 1 electron. We can analyze their electronegativities. All metals have very low electronegativities. That's 0.8 for potassium, because metals don't like to gain electrons, they like to lose electrons. Bromine is a 3.0. So they have a very different electronegativities. We always will see a big difference in electronegativity for a metal and a non-metal. The electrons are transferred. Potassium lost an electron, bromine gained an electron. So this is an ionic bond. It's not even a covalent bond, but it is so lopsided that the electrons are actually being transferred from one atom to the other atom. So we could compare it to polar covalent bonds. It's just like an extreme example because it's actually an ionic bond. So in a non-polar covalent bond, you've got two atoms with the same electronegativity. In a polar covalent bond, you've got two things with different electronegativities that are both non-metals. Ionic bonds, you will always have a way different electronegativity, and you'll always have a metal and a non-metal, but you already knew that.
Okay, here's a little model to help you understand polar bonds versus non-polar bonds. Here are two electrons. It takes two electrons to make a bond between two atoms, so my hands are like the atoms. These two electrons are the bond. If the electronegativity pull is equal from both sides, the electrons are being shared equally. Notice they're staying in the middle. But if I have stronger electronegativity on the right side, now I've got a stronger rubber band, stronger electronegativity on the right side, the electrons are pulled more to the right towards that atom. So they've got unequal sharing of electrons when the electronegativity of the two atoms is different.
Okay, back to a couple of examples. So for each of these pairs of atoms, carbon and oxygen, potassium and bromine, etc., we're going to analyze their electronegativity to help us figure out, is it a polar covalent bond, or is it a non-polar covalent bond, or is it some other kind of bond? Okay, so carbon electronegativity is 2.6. Where'd I get that? From table S. Oxygen, the electronegativity is 3.4. Okay, so what's the electronegativity difference? Well, 3.4 minus 2.6 is 0.8. They have different electronegativities. That would be an example of a polar covalent bond. Remember, a polar covalent bond is a lopsided covalent bond. Potassium and bromine, hold on, we've just been through this. They're a metal and a non-metal. Okay, and like we said, potassium was 0.8, bromine was 3.0 for its electronegativity. The difference is pretty big, but it's not a covalent bond. It's an ionic bond. Okay. Nitrogen and hydrogen. Nitrogen has an electronegativity of 3.0. Hydrogen's electronegativity 2.2. So the difference in their electronegativity is 0.8. They have different electronegativities. That's a polar covalent bond. Okay? Remember, polar equals lopsided. Chlorine and chlorine. Oh, two atoms of the same element. Okay? One has an electronegativity of 3.2. The other one has an electronegativity of 3.2. A bond between them has no difference in electronegativity. So that's a non-polar covalent bond. Okay, hopefully this is starting to make sense, and if you see, it's actually really simple. A couple more examples. Hydrogen and oxygen, 2.2, 3.4. Okay, the difference in their electronegativity is not 0, it's 1.2, so that's a polar covalent bond. Okay. Carbon and hydrogen, okay, they have a bit of a difference in electronegativity. They're kind of close together, but still they got a difference of 0.4. So that would be a polar covalent bond. Is it the most polar covalent bond? No, but it's still a polar covalent bond. Now, carbon and sulfur are kind of interesting. Carbon has an electronegativity of 2.6. Sulfur has the exact same electronegativity of 2.6. So the electronegativity difference is 0. So those are two atoms of different elements, but they actually have a non-polar covalent bond. Most of the time, non-polar covalent bonds will be between two atoms of the same element. But here's a case where carbon and sulfur have the same electronegativity. Okay. Now, just to wrap up, we looked at examples of nonpolar bonds where the electronegativity is the same. They're sharing their electrons equally. And polar bonds where there's a difference in electronegativity. The electrons are being shared in a lopsided way. But these are both covalent bonds. Now, the next thing we're going to learn about in another different lesson is what does the term polar mean for a whole molecule, not just one bond? Here's a water molecule. We already learned that water molecules are kind of negative on one side and kind of positive on the other side. Overall, water molecules have an uneven distribution of electrons. So they're slightly positive on one side. We call this a partial negative charge and a partial positive charge previously. That's just a delta symbol, means partial negative and partial positive. So overall, water is a lopsided molecule. It has a negative end and a positive end. In the next lesson, we'll learn about how we can analyze a whole molecule to figure out, is it a polar molecule, meaning lopsided, or a nonpolar molecule. But for now, you should go back to, so that's what we'll do in the next lesson, analyzing a whole molecule. But what you should do is go back to box 2 and box 3 in that Hyperdoc, go through some of those explore activities, and then try some of the practice. Okay? Thanks for tuning in.